Okay, so I'm back with the Roland here. This is the back of the circuit board. I'm looking at the horizontal drive circuit here, and there's these two transistors here and here, marked by these three pins here and here. You have the transformer here, the power transistor here, which drives the flyback, and the horizontal output, which is right here. So I'm looking at this circuit. I even pulled this top transistor right here and tested out a circuit, and it tested good. And I'm looking at it, since there's no schematics online, I'm kind of reverse engineering it in my head, and it seems to be a very peculiar circuit. So I have a positive line that gets jumped over from here. I think it's plus 15 volts, barely regulated. So it goes to here, and then there's a Zener diode from this connection here to this connection here. So that Zener diode goes across here with the cathode on this side, on the positive side. And then you have a resistor that goes across here. And this resistor goes to here and here, and this creates a bias current to this top transistor that's steady. There's a capacitor here and a resistor here to help smooth that DC out. And that just goes to ground there. So that creates a constant current to this bottom transistor, which is what actually generates the signal that goes to the transformer. And its constant current from this transistor drains this capacitor, I think it's across here, and decreases the voltage across it, causing its current to go down and lowering the current across here, because this connection here is the other side of the transformer, and it's positive, and it goes through two big power resistors and a smoothing capacitor and another regular diode, and that's how it gets its voltage. So whenever we get a positive pulse here, it charges up those capacitors, the beam flies back to the other side, we get a pulse of high voltage, and then it scans back across. But if we go and look at this circuit, there's nothing, no input to it except this resistor right here, which goes across here, and this resistor goes over to here to the connector, which is where the input is. And I believe that's the horizontal sync input. So this circuit, from the looks of it, has no way to be self-resonant or self-oscillating. So the only way to make it work is to actually send a sync pulse into it at the right frequency in order to make the deflection work and the high voltage work. And I don't think I've ever seen anything like that in my limited experience with cathode ray tubes. Granted, I am only 30, so I don't have a lot of experience repairing them except for the past maybe decade or so. This is kind of, I wonder if there's maybe a feedback signal that can be jumpered over here, and it's just more like end user programmable or in manufacturer programmable or something. Anyhow, that's all I've got on the Roland for now, other than it burning up its phosphor because I removed the signal from the input before turning it off. And even if I turn it off before removing the signal, that beam shrinks and goes very, very bright. So I don't even know if there would be any saving it from that, or maybe it plugged into some more proprietary circuit that automatically cuts the brightness first, because I even turned the brightness down on the potentiometers on this board and the external potentiometers, and the beam is still absurdly bright. And the only way to really keep it from burning the phosphor any further is to turn off the CRT before the source gets turned off, and that's risky there. That shouldn't even happen. So I think there's something else maybe wrong with this board. Clearly there is no self-oscillation of the horizontal drive here, as far as I can tell. I'm going to investigate this connector a little bit further, see if maybe there's something else going on. But that is kind of odd that it would be broken out like that, and there wouldn't be a circuit to keep it free running whenever there's no signal in, so that it still has deflection even when there's high voltage.